In this video, I'd like to go over the last term in our analysis of the conservation of energy equation, and it's one that we've been either told to neglect so far or we've just blatantly ignored, and that is the head loss term. This is the loss term to major and minor losses and all other things that can go on in a system. And to introduce this topic, I want to focus on a specific situation of pipe flow, and the reason for that is it's well quantified and we have a very good understanding of that, and it comes up again and again when we want to design pump systems and turbine systems. We always have to account for the head loss in the pipes when we're moving water or some other fluid around. Okay, so I'm going to start again, as we do with all our problems, with the full conservation of energy equation here in the engineering formulation that we use. And the term that we really are interested in here is this term over here, H sub L. And as with most engineering applications, what we like to do is quantify our terms into some easily measurable factors or coefficients and things that we can multiply together to get an estimate of that head loss, a reasonable estimate for a particular flow through a pipe. Okay? And that's been done. The equation that it can be derived, I'm not going to go through it here, is that H sub L is equal to some friction factor F times the ratio of the length of the pipe to the hydraulic diameter times a very familiar term, V squared over 2G, which is our kinetic energy term. Okay? So that gives us an estimate of the head loss. The one thing you need to be careful about here is that the V squared over 2G is not the term that we see here and here necessarily. You want this V here is the velocity in the pipe, right? So for example, in several of the examples we did, we had two reservoirs and a pipe in between them, and if we take the free surfaces at beginning and end point, V's are 0 because they're large relative to the flow going between it, and so the surfaces isn't changing much. So those V's might be 0, but the velocity in the pipe, however, is not, and so it's not the same velocity, but it is the mean pipe velocity. Okay? So we've introduced now two terms that you may have not seen before. The first one is the hydraulic diameter, and the second one is the Darcy friction factor. So let's take a look at those. The hydraulic diameter is very straightforward. It is dependent only on the geometry of the pipe, and its definition mathematically is it's equal to 4 times the cross-sectional area divided by the wetted perimeter, which is the perimeter of the pipe, the diameter or the length of that perimeter of whatever the pipe is, whatever shape it is, whatever the fluid is touching. Okay? And it's tabulated for a lot of different shapes in your book. And just to show you a couple of examples here, for a square pipe, it's equal to 4 times B times H, because the area of that is B times H of that square or rectangle, over 2H plus 2B. That's just the perimeter. You add up all the length of all the sides. And you can simplify that accordingly. For a circular pipe, it's actually even more convenient. We get the area of a circle, cross-sectional area is pi over 4r squared, multiplied by 4, you get pi r squared, divided by the wetted perimeter, which is just the diameter of the circle, the circumference of the circle, 2 pi r, you plug that in, you can simplify that, and it's really just the diameter of the circle. So it's very convenient to work with circular pipes for that's one reason they are anyway, to work with circular pipes. Other reasons are that it's easier to build clamps for them, it's easier to build fittings and things like that. So there are other considerations, but from a hydraulic standpoint, it's very convenient that we use circular pipes. Okay? So the Darcy friction factor is the other one that we haven't seen before, and this one's a little bit more complicated because this is where we're going to lump in all of this stuff that happens at small scales into some general head loss term. Okay? So the first thing we should look at is what the flow looks like in a pipe. And I've sketched out here two types of flow: laminar flow, which is a smooth, even flow, and I demonstrate that here. So if we wanted to measure the velocity in this pipe at this point here, and we looked at it in time, it's going to be consistent, it's going to be a straight line. It's always going to be the same in laminar flow. It's a very smooth flow. But we still have a gradient in velocity like this due to the no slip conditions at the boundaries. Okay? The other type of flow, turbulent flow, is going to have a mean profile that looks more like this shown in the figure. And if I take this same point, like here, and measure it through time, it's going to be really erratic around some mean velocity. But we take that mean. So that black line is that V bar. It's the mean. It's not what you'd see at all points in time, but it is the mean flow. Okay? And you can see, again, there's some shear here near the walls like this, and it's pretty consistent in the middle. It's a very different shape. And that's important because if you recall back to some of our very early lectures, the shear stress that is imposed on the fluid by the flow of it is equal to the viscosity times the velocity gradient. And so in this area, you're going to have some shear stress that acts along the wall like this. And same in the turbulent flow, you're going to have some shear stress. It's really kind of, it's analogous to friction. It's a frictional stress that acts to slow the fluid down because it's in contact with that solid barrier. Okay? So if we think about what the friction factor might be dependent on, it's going to be a function of the density of the fluid, the viscosity of the fluid, some length scale d, which is going to be our diameter or our hydraulic radius, and the velocity. And a lot of that arises from this tau. It's really a function of tau, but we have viscosity here, we have v here, and then this dz, our functional length scale there, is going to be that width of the... So it all comes in here where we have mu, v, and d, and then obviously the density is going to be important because it becomes important when we look at the energy. Okay? So what we know, because the shape of the profiles of the flow is changing, the friction factor is going to be dependent on the flow velocity and whether or not the flow is laminar or turbulent. Okay? And Osborne Reynolds, back in 1886 or so, developed what we call a non-dimensional number. It's called the Reynolds number. It's equal to the density of fluid times the velocity times the characteristic length scale d divided by the viscosity. And if you recall, look back at this, it includes all of these terms here, which is really nice for us. And for pipe flow, if the Reynolds number is less than approximately 2300, we have laminar flow. If it's between 2300 and 4000, it's what's called transitional flow, which means it might be laminar sometimes, and it might have little bursts of turbulence that go back to becoming laminar and back and forth. And then if it's greater than 4000, and for pipe flow again, the flow will be turbulent. And that's going to be consistent for whatever fluid you're looking at. And so what we're interested in is where the Reynolds number might be for a particular fluid flow. As we said in the previous the previous slide, the Darcy friction factor is going to be dependent on whether the flow is laminar. So what we end up saying, just like we did before, that F is going to be a function of the Reynolds number. Remember, because we pick up all those terms. So let's take a look at our three cases: laminar, transitional, and turbulent. Or for laminar flow, the Darcy friction factor is simply equal to 64 divided by the Reynolds number. Very straightforward way we calculate that. For the transitional case, it's a little bit trickier. It's difficult to determine because, again, the flow's moving from periods of being laminar to periods of being turbulent and back and forth. But what we end up doing is it's going to fall somewhere in between our laminar case and our turbulent case. Okay? And then finally, for turbulent flow, there have been engineers that have gone in and done experiments to calculate this, and they've come up with this empirical relationship where 1 over the square root of the friction factor is equal to -2 log 10 of k over dh divided by 3.7 plus 2.51 divided by the Reynolds number times the square root of f. And it gets a little tricky because f appears in the left-hand, right-hand side of the equation, which means we have to do iterations to calculate this to get the right f. Okay, so now we've introduced another thing that we haven't seen before, and that is k. And what k is, you'll either see it written as k or e or epsilon, and it's the roughness height. So it is the height of these roughness elements of the wall, and is dependent really on, one, the condition of the pipe. So if there's a lot of fouling, a lot of stuff growing, or it's rusting a lot, K will be very high, and the type of material: stainless steel, PVC, regular steel, cast iron, whatever the type of material is going to have a huge effect on this. And you can look that up in your book, or it's tabulated on the internet, and we can get some estimate of what that roughness height is for different materials. Okay? So basically, we've gone through today and looked at how to calculate head loss for the engineering formulation for conservation energy. And what we ended up finding is that H sub L is equal to F L over DH times V bar squared over 2G. Okay? So that's it. And then we spent a little bit of time going over how to calculate DH, and more importantly, how to calculate F, because this is going to be the key factor here, is how we calculate F. All right? So the next few videos, I'm going to do some examples of how we use this equation and our formulations for the friction factor to solve some engineering problems.